motor, and then what you are doing, then you have coupled this motor with some gear arrangement, and let's say that this is a differential gear, and then with that differential gear, the motor is the two wheels of the motor is connected. Okay, and this is receiving energy that is through the voltage source inverter from the DC bus. DC bus. So the two cases. In this case, you see that the tractive power, what is required to the wheel, okay, to the wheel is being delivered to the motor, and but it is indirect. We have a differential gear in between, and here you see that the tractive power is directly being given to the wheel, to the motor. So this is what it is there in the definition. Okay, so that's why it is written that to the wheels directly, okay, directly or through differential gear. Now, by receiving energy, you can see that either fully contributed by onboard DC source. Okay, this is one thing, or contributed in part by the lower side IC engine. What is the meaning? You see that one. There are two possibilities. That what will here you have the onboard DC source, which could be, let's say that for the time being you consider battery. Here I am putting a ground representation that for the onboard system you will not see that grounding is there. Okay, common neutral point can be there. Okay, similarly here the DC bus is formed by series connection of the battery. So this is one possibility. Okay, there is another possibility also. And what is that possibility? That here you see that you are receiving whole of the energy from onboard DC source. That is the battery here. Okay, onboard DC source. Now, another possibility that you can receive a part of energy from the wheel, from the IC engine. And what could be the possibility? The possibility is that, let's say that here I am drawing again. Let's say that this is a fuel tank. Okay, this is a fuel tank. Okay, and then this is giving energy to the IC engine, and with the IC engine, what is happening that a generator is coupled. Okay, a generator is coupled, and then this generator is connected with a electronic converter, which is let's say that AC to DC, and then this is giving energy to the common DC of the vehicle. So you see that here we are having an IC engine also. Now you have the two possibilities. You can receive from this battery also and from here also. Okay, from the IC engine. So this particular arrangement is called hybrid electric vehicle. Okay, hybrid electric vehicle. And when you don't use any IC engine, you do not have any IC engine, then we say it is a pure electric vehicle. Like this one is the case of pure electric vehicle, and this is the case of pure electric. When no IC engine is being used. Pure electric vehicle. This is what the definition is there. Okay. Then the thing is that, okay, next we go to the definition. Now, so we understand that from where we are receiving the energy. It could be onboard DC source, or we receive the energy from four sides IC engine. Definitely, if you are going to receive a portion of the energy from the battery, then what you will do that you will not use the fuel tank of that side. Your IC engine side will be.
Sir, your voice is not clear, sir. Please, little bit slowly. Little bit slowly.
So let me check. Just a moment. Let me check. Here I send it to the receipt. Maybe from here I send it. From my side, audio is full. Is it audible? Or hello?
Yes, sir. Okay, sir.
Okay. Now it is clear.
Yes, sir.
Let me make it clear. Okay. till now I explained the definition in which we understand that okay, there is a possibility of person to receive energy from onboard DC source, or we can receive energy from the lower side IC meter. Okay, as compared to the conventional IC based spectrum. Now, the thing is that then what is the objective? Why we are moving towards the electrification? So only like the motive, like the reason for moving towards the electrification are two basically. We want to improve the performance. If you see the dynamics or the efficiency of an electrical system, you will find that the efficiency of an electrical system is much better than the purely mechanical system. Okay, so we want to improve the performance. This is not only the one objective that you want to improve the performance, but you also want to reduce the which are being contributed by the consumer. So these two reasons that we want to reduce the pollution, and second thing is that we want to improve the performance of an electric vehicle. Okay. This is the situation. So let us understand how we are going to do this, to improve the performance of the vehicle. Yes. So let me go say. As I told you that we are having a conventional vehicle. Okay. So in that, what is the situation? We have a fuel tank. Then with this fuel tank, IC engine is connected, and then with this IC engine, the differential gear arrangement is there, and then it is connected with the wheel. So we all know that this is what mechanical power transmission is taking place. So efficiency of this sector, okay, this particular efficiency is very, very poor. So what we can do then? With what we can do, like, okay, we can use the fuel tank. Fuel tank is there. Then we are having again IC engine. With this IC engine, what we are connecting a generator. Okay, and then this generator, this particular we are connecting a generator, and then with this generator we have AC to DC conversion. Okay, AC to DC conversion is there, and then here we are having a DC bus. Okay, DC bus. And with this DC bus, our motor is connected. Okay, our motor is connected. Not this one. Motor is connected. This is here. You see the DC to AC conversion is there, and then we are having a motor. Okay, the traction motor is there, and then this motor, maybe consider the case of a single motor system. Okay, a single motor system operator. Then now you connect your, and then you are having wheels. Okay, two wheels of the vehicle are there. So if you see here to here, here this was the situation. Now, but if you compare the efficiency of the energy conversion which is taking place here, okay, up till this one, this is very good, very, very, very good. Okay, as compared to this mechanical. So what you have done basically, you have improved the efficiency of the system. So what will happen? For to drive the vehicle for the same range, now you are going to consume less fuel as compared to emission first thing that. Now, performance of this system, like in case of acceleration and other things, okay, energy recovery, so many things are possible now with this particular arrangement. Like if you think of electrical braking, right? So overall performance is now going to be better. So you can see here that under such a situation, you are going to improve the performance of the vehicle. So as you see that this is also an electric vehicle. Why? Because the final reactive power is being delivered over motor. So this is one of the examples where I can say that how you like you can say that it is possible to make the improvement in the performance. So you can see here like there are other possibilities also. Suppose that you want to have electric braking, it is possible. It is electric motor. You can definitely do. Suppose that regeneration is taking place, so you can definitely recover the energy. But important thing is that you cannot submit to this side, so you have to use some arrangement. Okay, maybe like you will be using onboard storage. Okay, or maybe some ultra capacitor system will be there. So different possibilities are definitely there. So ultra capacitor is connected with bidirectional converter. Okay, let's say that this is. So this is something like store that energy, recover that energy. Okay. So by this way, it is, we have the more dimensions to improve the overall performance of the vehicle. Okay, by improving the efficiency, you are adding other features such as like electric vehicle regeneration, all those things in case of electric. So this is a way how we can say that we are improving the performance. It is not like only this much is there. Suppose that what happens that you have heard about the electric vehicles in which we say that micro hybrid, mild hybrid, and full hybrid are there, and then pure electric is there. So what are basically these things? Okay, if you observe the situation, just one representation I'm going to make for you. Let's say the conventional vehicle is there. So conventional vehicle. Okay. Vehicle you see. So for that, I'm just putting here IC engine, and then fuel tank. Now what is happening? So one portion of the power is actually being delivered to the element, and this is you can say that transmission is there, and to which now your wheels are connected. Okay, so here I'm making wheels. Okay. Then what you do that you have the batteries also. Let's say that this is the battery. Okay, you have the battery, and then uh, maybe like you are using some power electronic converter, okay, and then motor, and then active power is used. So you can see that what are the different possibilities you are adding to your system. If you want, you can directly operate work in the electric vehicle mode. Okay. If you want, you can purely work with this IC engine. Okay. Second thing is that if you let's say that your onboard charge is finished, so if you want, you can charge your battery also on board. This is a case of hybrid vehicle. Suppose that you want some acceleration. Okay, you want some acceleration. So maybe like what you do that you are not interested in consuming more energy from the vehicle. Just let me see. So what we can do, suppose that you want to just start your vehicle. So at the beginning, what you will do is that you are starting your vehicle with this. Okay, means of course that these two are connected inside. Maybe some connection will be there, and then finally some connection will be there. So what you can do that you can give an initial speed to the IC engine. So you run your vehicle up to a particular speed during the acceleration, and then finally hand it over to the IC engine. So by this way, you are saving lots of energy also. Okay, not reducing the consumption of energy. So that is the case in case of let's say that when you do start it and like some micro hybrid. Then in mild hybrid you accelerate also up to some extent. In the micro you start here, okay, but in mild you accelerate also. Okay, you accelerate also. This is we can say that speed profile. This is time, and this is speed. So you are so in micro you only start your vehicle and then stop it. In mild you start it, then you accelerate also up to some extent, and then finally when you reach to the top position here of the profile speed, then what you do that you hand over the transmission of active power to IC engine. Okay. So that is called mild hybrid. In full hybrid, you will see that both would be working together. Next, during the normal running also. During normal running, both would be working. But here we have seen that during acceleration, we are working with the motor. So under such a situation, when your purpose is only to accelerate this point here, accelerate here, okay, or here start and accelerate, then under such a situation, these motors are called booster motor. Okay, booster motor. And booster motor have like they are very high power rating, okay, but they cannot continuously work with your system, cannot continuously run because they are designed to deliver very high power for short duration. Okay. and most objective is maybe the acceleration for let's say 0 to 10 seconds, 20 seconds. Okay. So that purpose is yeah, basically. Okay. So I think I have explained so many things about you about some things about the electric definition of electric vehicle and hybrid electric vehicle and its objective. Let us move further. Let us move further. Now, then we try to identify what are the different components of subsystems of an electric vehicle. If you see the electric vehicle, you will find that there are onboard batteries, and a motor controller is kept there, and a motor is there. This is the main thing you will see. Then, of course, inside the motor controller, you will see that some control circuitry are made. Some sensors will be there. So we can classify like this, it whole of the electric vehicle system into multiple subsystems. And what are those? They can be your supply system, okay, yeah, traction system, control and monitoring system. Okay, in traction system, you can see that like you are having a traction motor together with a voltage source inverter. Please remember that if your traction motor is an AC, then only you will be using a DC type, then only you will be using a voltage source inverter. If your traction motor is a DC motor, then you have to use a DC converter. In supply system, you'll find that the different possible energy sources are there, and those energy sources are what? Like they can be like onboard battery, they can be your fuel cell. It could be a fuel cell. Then it could be photovoltaic panel, PV panels. Okay, these are the energy sources. Okay, these are energy sources. So I'm writing here. Yeah. Okay. Then there's a possibility that we will be using combination of battery with ultra capacitor then with ultra capacitor or combination of battery photovoltaic panel with ultra capacitor or combination of these with the ultra capacitor. Okay, and then another possibility is that we can use flywheels also. Flywheel also. So these are basically power sources. I will explain you the definition. Energy sources and power sources. So there is a possibility that we can use the combination of energy source together with power source. So there it comes the concept of hybrid energy sources. Okay, so I will explain those parts also. So you will be seeing such type of arrangement here in the onboard vehicle. So in some cases, you will observe that you don't need any power from circuitry arrangement. That when you are operating with the battery only. Okay, but when you will be operating with fuel cell, photovoltaic panel, or combination of ultra capacitor or flywheel, then under such a situation, for you it is mandatory to use this power electronic circuit arrangement. Okay, what is the purpose of use of using this power electronic circuit arrangement? One purpose is like very important thing is to know that these traction motors are designed for higher terminal. Why you keep higher terminal voltage? If you are keeping higher terminal voltage, then you are reducing the performance. This is one of the reasons. Okay. Then, but the other side, if you see that these batteries, so here what is a higher terminal voltage, so DC voltage are high voltage. Huh? Okay, high voltage. So here also it is high voltage, but is another issue with the energy source is that here the voltage is low. But because they are able to deliver sufficiently large current, which is required for the traction, even at the lower terminal voltage. Okay, so there is a mismatch between the low voltage of the source and higher voltage of the DC. So to bridge this gap, we need to do this power electronic converter here, boost converter. Okay, this is one of the reasons. But in some of the cases where you want to recover the energy or assist the battery, okay, like assist the battery. The first I tell you the recover of the energy. So whenever the recovery will take place, what? Regeneration is going to take place, and that energy should be bypassed somewhere. Okay? Because you don't want to submit to the battery, maybe a portion you want to submit to the battery, and rest you want to bypass it. Okay? So under such a situation, again, power is reset. And what would be the bypassing? Maybe like you don't want to recover that energy, rather you want to dissipate it, like dynamic braking. Okay? So you want to dissipate it because why you want to dissipate it? There's a possibility that you are running your vehicle with fuel cell, where energy which you cannot submit back the energy. Or there is a possibility that your vehicle is of this type, IC engine is there, okay, but the main source is IC engine, and you cannot submit back the energy to this type. So you have to bypass it or dissipate it. Okay. You have to dissipate it. So maybe you are storing it, or maybe you want to dissipate this to the resistor. All these possibilities are there. So wherever recovery is not possible, you will dissipate it. Okay. So for that purpose also you need to use all electronic circuit level, because you want to make controlled conversion. Okay, there. A controlled power flow. So this is the what about the supply system. Then you are having control and monitoring system. We know that what is the purpose of control and monitoring system. We need this because we want to monitor the different variables which are there on board. Maybe that terminal voltage, the phase current which is required to be injected, what is the battery state of charge, so all those things. Okay, battery health. For everything we need to have the monitoring. So for that purpose we need sensors. Okay. And what we do that we have some driver circuitry also which are required to be operated based on the reference what we are giving. Maybe the torque reference, maybe the speed reference. Okay. So that like accordingly you can figure the switches of this or operate the switches of the maybe the voltage source inverter here, or maybe the power electronic circuitry arrangement which is here in this case. Suppose we need for that driver circuitry also. So this is the objective of the control and monitoring system. Okay. Then next question, this is what we have talked about is onboard system. Please remember. Then you replace when we talk about a pure electric vehicle. Concern is that here we have only onboard DC source. What you will do then after running some time, okay, you will lose your charge. So again you have to charge. So for that we have the offboard system. Okay, so what is that offboard system? In that you will see that here you are having okay, I'm making it there. Okay, it could be anything also. Grid is there, and then with this grid you have let's say like a EFC rectifier circuit is connected. Here you are having the DC bus. Okay, with this DC bus you can have a charger also. You can have a charger. You can have a charger. This is the charger. So this particular arrangement is called a charging bus, okay, or charging system. Okay. So supplying the so overall subsystem could be what? Supply, traction, supply system, traction system, control and monitoring system, and then charging system and charging system. These are the different subsystems of an activator. Now let's see. Now let's go ahead. Now about this charging system, let me first explain. Then we will again discuss in detail. So as I explained, that there's a two possibility with the like here the charging system here, what you are seeing here, there are two possibilities. The charger what you are seeing that could be conductive or that could be contactless. Okay. So once again let me draw the diagram. So this is a grid. Okay. This is a grid. This is a grid. Okay. This is this is the let me make it very large. And then this is AC bus. AC bus. Then what we are having power factor correction rectifier, ESP rectifier. Okay. And then here we are having a DC bus. Here we are having a DC bus. Okay. And to this DC bus, a charger is connected. Charger, and this charger is now giving energy to the onboard battery. And here I am putting ground. Please note that like you can have common user but cannot be the ground. But for the sake of single line diagram, I have used it. So this battery is onboard. Okay, here I am battery. This is on. So this is the arrangement what you are seeing. Like this could be maybe like here you will see that you are having a buck converter. Okay, here. So just for the representation, I am drawing for you. So this could be the arrangement. maybe like we need again a filter inductor because we need to connect it with the battery, because the battery could be working with the constant current mode, constant current, constant voltage charging like this. And this is the lecture that this is the this is bus voltage, and this is the switch. So like, and here I found the non-isolated arrangement. Maybe isolated arrangement also. So this is like a case of a conductive charge. Okay. Now, second thing is that other possibility is what? Like if we have the same situation, but in place of this DC bus, like if we have DC bus and connection with it, now you can have this is that okay, and you have the AC bus, maybe like same PFCR you're using, power factor correction rectifier you're using, and then now here and with the DC bus, what you're doing that an H bridge converter is used. Okay, H bridge converter. Okay, this could be like the most simple arrangement like I'm drawing here. Okay, one of the case. Huh? This is that, and here it is the DC bus. DC bus. Okay, and with this, I'm not drawing the body diagrams. Consider that the body diagrams are there. And with this arrangement, here you see that this is the H bridge, and then you will find here that some compensating circuits are there. Okay, compensating circuit. What could be? That could be inductor, or those could be capacitors, and they can be connected in series or in connection with in parallel with a coil. Let's say that this is the coil. Okay, this is the coil. This is on ground, and then what will be happening? That there's another coil will be there. Another coil will be there. This could be 10 to 20 centimeters. Okay. Generally, people keep out 10 to 15, let's stop for 10 to 20 centimeters. And then again, here we will see that you are having a compensating circuitry, and that this could be in series or parallel with the coil. This is a capacitor. Okay. And then here we will be having a high frequency rectifier. Okay. And then some filter circuitry. I should not draw two lines. Then yes, some filter circuit could be there. Okay, maybe a capacitor, maybe some inductor or something. Okay, so we are looking at compensating circuit. Huh? Compensating circuit. Here also compensating circuit. And then this is connected to the onboard. So what the arrangement here you are saying that you can see there is no physical connection between the onboard battery and the grid here. So this is the case of a wireless charging. Okay? Wireless charging. Wireless charging. So like if you have any doubt here, this is a possibility that this is the main coil. Okay, main coil is there. So you can connect your capacitor in series. You see, this is that coil. Okay, so this is called. Okay, if the same arrangement is used here in this like here, this is the secondary coil here. Okay, this is called, you can put receiving coil, and this is called transmitting coil. And here also, if you put a series compensating circuit, then it is called SS topology. Understand? If in place of this series, suppose that what you do that you put a parallel capacitor, let's say. Okay, if you put a parallel capacitor here, okay, parallel capacitor, it will become SC topology. Okay, maybe like here you want to use some parallel arrangement. Okay, like this, and then this will be P topology, you can say, or like maybe like here we are using. Sorry, capacitor, series capacitor. This is the series capacitor. So it will become a PS topology. So just a basic I explained you. Otherwise you can use some other comparison. Maybe one coil here, an LCL topology. So by this way, how this coil compensating circuit, the coil is arranged, you can give the name of different compensation topology. But what is the reason of using this compensation circuit? The reason of using compensation circuitry is that this is an air here. Okay, so what will be the mutual inductance? That is going to be very, very poor. So you want to improve this one. Okay, one thing is that you want to improve it. Okay, and if you see that what is the formula, it will be omega x sorry, omega n, and then this is going to be 2 pi f. Okay, whatever the mutual inductance is coming. So I am writing here. Just a moment, 2 pi fm. So you can see that you are seeing that the frequency term is coming. So you will see that when we work with the wireless power transmission, then here we operate at very high frequency. Why? Because if you keep this frequency high, then automatically you are going to improve mutual inductance. So here that you will see that the frequency of operation will be very high as compared to the conductive charge. Maybe like 85 kilohertz to maybe like 90 kilohertz. 99, sometimes 95 kilohertz as per the standard. So this configuration, what you are seeing, this is called wireless power transfer, okay, or wireless charging, or contactless charging. This is called conductive charging. Okay? Conductive charging. So I hope it is clear to you. In some cases, you will see that people also use, in place of using like this, you see that demo control is there. Okay. So in place after this filter, people sometimes use this type of arrangement here itself on board. Okay, so that they can make the control. About the PFC rectifier, I'm not explaining you. Okay.
Sir,
So this is what the
sir, one question.
yeah.
Sir, you said that if it is a one capacitor, if you're using a primary side is a this winding, so you have to place the capacitor at parallel primary side. Capacitor positions. So if it is a bidirectional converter, then where we have to place this capacitors across this transformer or wireless transformer winding.
This, no, see, if you want to make bidirectional power flow, then accordingly you have to select this. You see that this arrangement here, you have to make some bidirectional arrangement. But here your topology can be your SS, SP, and these things are required to be evaluated. It is not like that for all the topology, for all the cases, same strategy, same compensation is going to work. So what is your requirement? Accordingly, you have to evaluate your SS or SP topology or P topology. Understand? So that is the case of evaluation basically. For your case, like for what you are working. So, but in any case, what we do that we first size the system, then calculate what should be the inductance and mutual inductance. Then after we start designing the point. Okay, that is done. Then what we do that we try to think of the using compensation circuitry so that we see that like if it is possible to improve that mutual inductance or not. So different compensation strategy will give you different type of improvement, and it is you who has to decide that which is most suited for you. Just I'm putting some nomenclature here for you. Okay, like this is the way how we do the nomenclature. So I hope you understand here, and again I will come back to this slide later. Okay, let me go ahead, and then again I will come back later. Okay. So and then what are the different configurations of onboard supply system? So as I told you that when you see that there's a battery, you will see that on the series connected batteries are there. Okay, series connected batteries are there. You will not find that like let's say that this voltage bus voltage here, this is a DC bus, huh? This is a DC bus voltage. Let's say that is 48 volts. Okay, this is 48 volts. You will never see like so what you will do that to make 48 volts, we have the 12 volt battery, so 12 volts multiplied by 48 volts. Let's say that it is 100 amps. You will not see that people are using, let's say that only one battery and 12 volts and boosting it. Okay, let's say this is the step of and then making it to 48 volts. There's a difference between the two. When you see that here 4 times you are making boost, 4 times you are making boost, 4 times, and here no boosting. What is the issue there? Suppose that here you are using 100 AH battery, 12 volts each, and the traction requirement is what? Let's say that 20 amperes. 20 amperes current is required. Because series connection is there, you see everything is okay, 20 amperes you are drawing from the battery, but if you make a boost here, let's say that here also you have used one battery of 100 AH and then you boost it into 48 volts. What will happen? Let's say that this side current is 20 ampere. What will be the current on this side? It will be 4 times higher 80 ampere. Continuously you are going to draw 80 ampere. Okay, one problem. In this case, the 100 amp battery was there. You was running 20 amperes. So how much hours you can run your vehicle? 5 hours. 100%. In this case, how much hours you can run your vehicle? 100 Ah divided by 80. You can see that less than around 1.25 hours. Okay. So if you want to run your vehicle in both the cases equally, then what you have to do? You have to increase you have to use the higher AH battery. Then only it is possible. So maybe like instead of 100 AH, you have to use now 400 AH battery. So 400 AH battery is 400 divided by 80 is 5 hours. So now you are going to use to run your vehicle. So you can see that earlier you were using 100 AH, now you are using 400 AH. The issue is that there's a linear relationship between the AH and the weight of the battery. Okay? Linear relationship. For make the double AH, weight will be double 4 times. So you don't find any benefit in the power to weight ratio. Unnecessarily you are increasing the control component. So that's why you don't see that people use this boost circuit arrangement. Okay. Then where to use this type of arrangement? We use this type of boost converter arrangement for the cases where you see that the output characteristic is varied. Like for the photovoltaic panel with the solar insolation. This is you see that if the solar insolation changes, so you can find that the characteristic is varied. Okay. And what is your objective? You always want that you should track the maximum power point. So maybe like in this case it is here, maybe like in this case it is here, maybe in this it is here. So you always want to track the maximum power point. Okay. You need to use some circuit element, otherwise you cannot do it. Okay, one thing. In case of fuel cell, you see that when it is loaded, okay, you will find that the voltage is low. When it is lightly loaded, the voltage is high. That's the problem. You need to maintain a particular operating. It's a 48 volt you have to maintain. Okay, so in such a situation, it is important for you to use some power electronic circuit element. Understand? So that's why for wherever you find that the output characteristic of a source is varying in nature, there you have to use a power electronic circuit element, maybe like a boost converter in this case. Okay. Then we also see some of the cases where we have to use some power electronic circuit element, like some configurations. Understand? This is source is connected in series. This is source is connected with the traction system through a boost converter, and here you see that you have the multiple sources available, maybe a battery, fuel cell, or photovoltaic panel together with ultra capacitor. So because you see that the ultra capacitor is now used, so why we are using it ultra capacitor? Because we have to maintain this voltage here. Okay. First thing. Second thing is that suppose that this voltage is 48 volt, you will find that always we also use our capacitor of 48 volt. Okay. This is the 48 volt. Okay. It is not like you are using 24 volt, but we are using this because we need excess current whenever we need to go for the acceleration. Okay. So for that purpose, this ultra capacitor assists our battery. Okay. What will happen if this is not there? What will happen? You are going to accelerate. So normally you know that if the nominal current requirement is 20 ampere, when you accelerate, you will be drawing what? 40 ampere of current. Okay, 20 ampere, this is a 40 ampere of current. So under such a situation, what will happen here? You see, if this is not there, so you remember that you know that the characteristic, IV characteristic of a battery. So it is depending upon your speed at what rate you are trying to draw the current, the voltage drop takes place here. Okay? Maybe that as a normal running condition, this was the situation, but when you started drawing heavy current like this 2 times higher, you see that there is a drop in the bus voltage. You need to maintain this bus voltage also. Okay, you need to maintain this one. And how you can maintain it? That whatever the excess current is required, you can supply that current from another source. Then the bus voltage of this battery is not going to get affected. This is one of the reasons. Okay, so we need to use this hybridization. There are other reasons also. Okay, Then, use of ultra capacitor or any other arrangement of improves the life of the battery in terms of reports. That I will explain you. So these are some benefits we see that why it is necessary. Okay. Okay. Then what is the necessity of using this? You see that here. You see that we have used two sources here. What is the necessity? As I explained you that what are the different possible sources? Battery, fuel cell, photovoltaic panel. These are the energy sources. And what are the power sources? Ultra capacitor and the flywheel. You can consider the flywheel looks like something like this. This is the motor and the machine motor, and then here a high inertia disc is mounted. Okay, high inertia disc is mounted with the motor. And this is the DC bus. You can consider. This is a flywheel arrangement. Like one of the arrangements you can say. Flywheel arrangement. See. So let us say we have the energy sources and power sources. I explained you. Now, what is the energy source like? Generally, you see that if we say an energy source, a source is energy source, if its specific energy means watt hour per kg is much higher. Okay. Power source, their watt hour capacity will be very, very low. Okay, then energy density will be low. But in case of power source, you will see that the power density is high. You can see that high power density is there, but energy density. What does that mean? If you have a high energy source, then you can run your vehicle for a long duration. Because these sources are able to give you a nominal current, say 20 amperes, maybe for hours, 2 hours, 3 hours, 5 hours like this. Okay? But they will not be able to give you, let's say that you want to replace of the 20 ampere nominal current, you want to draw 40 ampere or 50 ampere. They will not be able to give you that much high current for the long duration. For short duration. Long duration, definitely they will not give you. For short duration, it will be difficult for those sources to be. Okay, but these power sources, what is their characteristic? They are able to give you very high current, maybe 40 ampere, 50 ampere, or 100 ampere for a very short duration of time, maybe 10 seconds, 20 seconds. And that is needed when you need acceleration, when you go for acceleration under such a situation. Okay, but they cannot give you continuously 20 ampere for long duration of time. They cannot give you 20 ampere for a long duration of time. These sources. Understand? So here, one side we have a source which can give us nominal current for long duration of time, and another side we have a source which can give us a very high current for a short duration of time. Okay. So we have the two requirements in a vehicle. One is that we want to run a vehicle for a long duration of time. Second, whenever we want to accelerate the vehicle, we should get a very high current. Okay. Raja Reddy, you want to annotate? Raja Reddy? So that's why for a supply system to have such a characteristic, this is a supply system. This is a supply system. Okay? This is our supply system. To have such a supply system which is having a capability of both delivering high current and nominal current. Okay? We do hybridization. Okay, hybridization. It's a fuel cell for high energy density, and then we have ultra capacitor. You see that? So, yes, Raja Reddy, you want to annotate? So, what we do that we do the so what is the operating point now? It is here. Okay, so high energy density and high power density. So that's why we need the requirement of hybridization. So, like here you have shown for energy management, but same thing is equally applicable for off-board energy management with the charging station. Okay, with the charging station. So I hope you understand why we go for this type of hybrid energy sources. Okay, but go ahead. Okay, there are different possible sources are available. Examples are there what we have in the laboratory. like the electric car, you can see here we have a battery, and then backside one motor is there. Then electric bike is there. Here we have a traction motor, and then inside here we are having a battery, having battery pack. Similarly, the car is there. In which you see that photovoltaic panel is there, and as well as the battery is here. Just a moment, huh? Hello. Similarly, we have like you can see that this cycle is there where we are having one battery and then a motor is traction motor there. This type of battery is called electric assisted bicycle. Okay, and now here you see that this is replaced by a battery is replaced by a hydrogen fuel cell, helium fuel cell, and then this is a hydrogen tank, and here this is a fuel cell, and then this is the power electronic circuit arrangement like this one. And then here this example you can see here on top we are having photovoltaic panel, and here we are having ultra capacitors. Then we have the battery here. The ultra capacitor and the battery. Okay, so here you see that three multiple sources are available, and these are some power electronic arrangements like the DC to DC converter for the ultra capacitor, and the bidirectional converter for bidirectional DC to DC converter for ultra capacitor, and then DC to DC boost converter, okay, unidirectional for this photovoltaic panel. All are here. Okay. Now, you can see here that this is the hybrid energy storage system. What I am telling you, so here battery, ultra capacitor, and photovoltaic panel. All the three sources are there. You cannot submit back the energy to the photovoltaic panel, so you use the or DC to DC boost converter, unidirectional. And here ultra capacitor we use bidirectional because whenever acceleration is needed, you can submit the energy to the motor, and whenever you are doing the regeneration, you can submit back the energy. You can submit back the energy to the ultra. We use this ultra capacitor. If you don't use this bidirectional converter, what is going to happen? You see that energy stored is 1/2 CV square for this ultra capacitor. So if you don't use it, what will happen? As it is going to submit the energy, the bus voltage is going to drop. Okay. So it will not be possible to deliver the maximum possible energy. So what we can do? You can see that we can write here. Okay. If you maintain this difference constant by maintaining one voltage, let's say that you maintain this voltage constant, VO as constant. So this is, even though it is dropping, the difference, this VO minus VI, this will remain maximum. Understand? This will remain maximum. Otherwise, in the previous step, what was happening? If you don't use it, this voltage is also dropping, and this is also dropping. So you will not be able to submit the maximum possible energy from the ultra capacitor. That's why you need to use a ultra capacitor or a bidirectional converter, so that you can fix at least this voltage. So this drop is definitely taking place, but you can see that this is going to be 0, 1/2. So we have kept this fixed. So because the two both are not varying, and you kept constant, so it is possible that you can deliver more energy. Okay, just a moment. Okay, so let's say go ahead to make a discussion about the charging system. Charging. Okay, so in charging, what happens? Understand the definition. It is a process of submission of energy to a battery by forcing current into it is called charging of a battery. You have a battery. Okay, battery pack. Let's say you have a battery pack. So what you can do that you can you have this source. Difficult to submit the energy into the system unless you apply a higher voltage. Then only it is possible for that higher voltage must, or you ensure that a constant current is being forced or injected into the battery. This is the reason why you are keeping the higher voltage here. Okay. So that's why we need to do this one. So different strategies I will explain, but the process of submission of charge, submission of energy to the battery by forcing current into it is called charging. Then what is the fast charging? Maybe like suppose that you are having a battery of 100 Ah. Okay, 100 Ah battery is there. So generally normal charging is termed as C by 10. C is the capacity. Yeah? So then C by 10 is what? 10 ampere. So if you charge this battery 10 ampere, let's say that this is 100 Ah battery. Yeah? 100 Ah battery. This is a 48 volt battery and each cell is of 100 Ah. This is each battery of the whole battery pack. It's a 4 batteries are used here. So if you're charging with 10 ampere only, it will be normal charge. Okay. But let's say that you charge it with 20 ampere or 50 ampere or let's say that 100 ampere. 100 ampere. So what you are doing, that you are injecting more and more current. So this will be what? It will be 2C by 10, so 2 times faster than the normal charging. It will be what? 5C by 10 is 5 times faster than the normal charging. Then it will be 10C by 10. So it is 10 times faster than the normal charging. Okay, so this 1, 2, 5, 10, these are called the degree of fastness. How fast you are charging the battery. Simple meaning is that if it is 100 Ah battery, you charge it with 10 ampere, so it will take around 10 hours theoretically. Okay, if you charge with 100 ampere, it will take 1 hour theoretically. So injection of the charging current into a battery which is charged at a rate higher than C by 10 is termed as fast charging. Okay, and the degree of fastness can be higher or lower and is represented by just what I explained you, AC by 10. Let's go ahead. Then different charging levels are there: level 1, level 2, level 3. We all know about it, so I'm not going to say anything much more about. But please remember that level 1 is for your house and offices. Level 2 is for the charging station, maybe at a private place, or maybe at your home outlet. It's like okay, garage or somewhere like this. And level 3 charging is the basically a charging. The more the power will be, the faster you will be able to charge your vehicle. This is depends on how much current you are injecting. Let's go ahead. Now, if types of charging is what? Like if we can have a static charging, or we can have dynamic. Okay. Static charging is what? Both the vehicle and the charging point. They are stationary. This is point and the vehicle. Both are stationary. But here the dynamic charging basically the vehicle is there and it is moving over the coil. Okay, wherever it passes over the coil, it gets charged. Okay, so this is the case of a dynamic charging. There are other dynamic conductive charging is also there. You have seen some YouTube videos, like in which you see that this is the road and vehicle is running on the road and some pantograph is down now. It is connected with the rail which is there now. So this is conductive dynamic charging. The truck is continuously getting charged to the rail which is there on the ground, but with the ground. Okay, so this is conductive dynamic charging and this is wireless dynamic charging. Then you can have a capacitive charging also, like flash charging. You have heard about the name. In flash charging, what happens that the bus stops there, and then that pantograph will come out and it will get connected with the pantograph here. Okay, so it is getting connected. You see here. Okay, you see here. So what happens that inside you have the ultra capacitors. Ultra capacitors have a very what you say that low impedance. So in a flash, they receive the energy, and finally you dissipate that energy to the battery. And the two purpose will be there now. Dissipation. One, it will give some energy to the battery purpose, and second, some will be given to charge the battery. But like what will happen? The energy it has received here to the vehicle, it is sufficient to run the vehicle maybe for 2 to 4 kilometers. Okay, for the next charging station. So the size of the accordingly you have to size your onboard ultra capacitors in the battery. Of course, in this case, size of the battery decreases. So that's the capacitive charging. Then there's the capacitive dynamic charging also. Like here is the wheel. Okay, and this is let's say that this is the wheel is there. Okay, and then this is the ground. So in the ground we have the capacitive plate here, and then here you can see the beam of the beam is there. Okay, so when it comes in contact, like in utility, you can see that this acts like a parallel plate capacitor. Okay, so that energy transfer. You know that what is the P? Like this is a parallel plate capacitor equal to external material. So when they come in contact, there will be an electric field in between, and electrostatic energy transfer takes place. Okay, through the electric field. Means the configuration could be just let me go back and then I explain you. Here I have explained this. So maybe the possibility here I have so this AC answer. So in place of this possibility, this AC will not be there. Know that one. Now in place of this one, you will see that you will be having plates. The plates will be there. Understand? One plate will be here and another plate will be on the top. So let's go ahead. Okay. So this is what I explained you before that for inductive wireless power charging, there is a grid and power factor rectifier has frequency water. That compensation circuit is there, the coil is there, then inside compensation circuit is there. Okay, and then the rectifier is there. Okay, and then battery is there. Now, there are different types of charging or what? They're like, we say that it is a continuous current charging. This is what is a continuous CV charging, constant voltage charging. And then you can see that you can have continuous current charging and constant voltage charging. And you can have pulse charging, like you see here, pulse charging, or you can have reflex charging. Okay. In all these cases, in this case or this case, temperature is not in temperature control is not in our hand. You give the current, okay, depending on at what rate you are injecting the current, battery temperature is going to rise. Okay. But here, there's a possibility of regulating the temperature of the battery. Okay. See, you set a maximum temperature. So when you are charging, what will happen? Battery temperature is going to rise. When you see that okay, it reaches to the maximum level, you will reduce it. Okay, stop charging, so temperature will go down. Or again, it will go up, and then temperature regulation is possible. Okay, this is the case. Maybe like what happens that some people do that depending upon at what rate temperature is rising, they decide the width of this pulse. Okay, on pulse or off pulse, means charging or no charging, non-charging. Like this side. In some cases, you will see that they will fix this. Like this is always fixed. Okay. So of course, like having a different fixed level or different level, it has a different impact on the charging time of the battery. Why? Because you see that this is I and this is P. So area of the curve will be what? This is the total charge submitted. Here area of the curve is what? Total charge submitted. Here this is I curve is there. So total charge submitted. And understand. So accordingly you can decide it. But one advantage is that it's possible for you to regulate the battery. Okay. Again, this is a reflex also in which what happens, we charge for some time and then we discharge. So this is not this much time, very for very short duration of time. Understand? Very short duration of time. For very short duration of time, you discharge also. Why we are doing so? Because you want to maintain the equilibrium in the chemical reaction what is taking place there inside. And this helps you in also uniform distribution of the heat. Okay. Then other advantages, if you use this pulse charging, in case of lead acid battery, they help in reducing the problem of sulfation. What happens that if you continuously discharge charge, then you find sulfates are getting formed in plates there. Okay. Means some sulfates are not getting dissolved properly, so they will get deposited. So because of that, what will happen that like capacity of the battery reduces. Okay. Similarly, in case of lithium-ion battery, you find that with the due time, like dendrite crystals are formed there. Okay, and if they keep on going, they will short the terminal. So capacity of the lithium-ion battery is also used. So this type of arrangement, reflex charging, helps in reducing the formation of dendrite in lithium-ion battery, and this pulse charging type of arrangement helps in uh, reducing the issue of sulfation in case of lead-acid battery. Okay. Let's go. Then there are some issues with that, like it is like you go with the fast charging, there's no problem, but there are some problems with this user. Okay. So what happens that if you increase the charging current, okay, charging current, the temperature of the battery is going to increase, which affects the life of the battery. So for that, this is the arrangement. What is the impact? You can see that suppose that you are increasing the charging current. Here you see that this is K. Okay, K. So 6 stages, let's say this is 2 times faster, 4 times faster, 6 times faster, 8 times faster, like this will be. So what will happen under such a situation? If you increase the rate of fastness or degree of fastness or injection rate of the current, your SOC is going to increase. Okay. But please wait here. At the same time, your battery temperature is also going to increase. Okay, see? And we have the limitation here, 50 degrees Celsius. Around 50 to 60 degrees Celsius is specified from the manufacturer. You cannot increase the temperature beyond this now, 50 to 60 degrees Celsius. So what is the limit now? 50 to 60 degrees Celsius. You see that by this time, what is the SOC is available? Let's say in this case, for this case of battery, your battery is going to get charged only with the limitation of the temperature to how much around? It could be around 35. Okay, or 35% SOC. You see, you have increased, let's say that battery is 100 AH battery, let's say, huh? So you are around 3.75, so you are injecting 37.5 ampere of current in place of 10 ampere of current, 10 ampere of current. So the battery is SOC is definitely increase, the temperature also rise. So after this, you cannot do it because they say that you should not increase the battery temperature. Okay, so this is the limitation. Now consider another case. Let's say that this is a case of a lead acid battery. Yeah. In case of lithium-ion battery, you see that this thermal time constant of the lithium battery is larger. So what will happen? The temperature rise will definitely take place, but it will take some more time. It will take some more time. Understand? It will take some more time. So what is happening? You see that you can inject a lithium-ion battery with a higher current, with 20, 40, 60, 70, like this, 70 ampere in place of 10 ampere. You can see. So lithium-ion battery, because they have a low thermal time constant, so you can inject higher current to have the same temperature rise. Like here, you have the same temperature rise. Under such a situation, you see that you can increase the SOC of the battery to around 70%. You see, 70%. But in case of lead acid battery, it was able to reach only 35%. That's why we say that, like in the case of lithium-ion battery, it's possible to inject a higher current. You sometimes say that people charge it with 7 C by 10 to 8 C by 10. Means if you have 100 AH battery, you can charge it to 70 to 80 ampere. And in some cases, people say that they can charge beyond 10 C by 10. Means if 100 AH battery, so beyond 100 ampere. Means maybe some people say that 20 C by 10. If you charge it with 20 C by 10, how much time it will take to charge the battery? 30 minutes. But you have to take care of the temperature. Okay. Now let's see about the temperature. What is happening with the temperature? This curve shows you that here you see the operating temperature, and here how much month you can use the battery. Okay. How much month you can use your battery here. So if you operate your battery at around 50 degrees Celsius, you can see that you can use your battery around 12 months. One year. Okay. 12 months. If you operate your battery at 30 degrees Celsius, you can see that here you can maybe like 42 months, means around 3.5 years. 3.5 years. Here 1 year, and here we are using 3.5 years. Okay. So what is happening that just having the control over the temperature rise of the battery, we can extend the life of the battery. Okay. So like for that purpose, we need to use cooling arrangement. Cooling arrangement is good when you are discharging also, or discharging means you are running your vehicle. Okay. Or you are charging also. For both the cases it is good. But let's say that during the discharge, when you're running your vehicle, you cannot, you will not be able to regulate this one, discharging of that. What you can do that you can use another source also, so that you can save the current. Okay, save the current. But you cannot control that discharging process. If you need 20 Newton meter, and for 20 Newton meters, there is acceleration, let's say that we need 100 ampere of current, for an example. So you have to get the 100 ampere. You cannot regulate that one to 50 ampere because torque, getting the torque is your priority. Okay. So we are not talking about that one. So, but what we can do during the charging process, definitely, with the proper charging strategy, you can, temperature regulation, you can improve the life of the battery. Understand? So you have the two factors. One, regulation during the motoring action when you are discharging the battery. So for that, you need to do the cooling, whatever the life is there. Okay. And second one is that you are charging the battery. So for that, whatever the light is getting through. Okay. So during the charging, you can use cooling arrangement or you can use some circuit arrangement, some control arrangement. Or charging code plus charging to regulate the battery. This is what you can do. So regulating the life of the battery. Let's go ahead. Okay, I think I'm running short of time. 12 minutes are there. So there are some issues. Okay. You can see here, like this is I am talking about the charging station now. So let's go here. Let us consider that this is the situation now. So we have the, let's say that this is the charge. We are talking about the charging station. Okay, and at the charging station you are having a DC bus. No need to explain the same thing again. We have discussed this. Let's say, okay, multiple charges now vehicles are getting charged. Multiple vehicles are getting charged here. Okay, multiple vehicles are getting charged here. Let me make it 3 on. Okay, multiple vehicles are getting charged here. So what will happen? So if you want to draw or charge more and more number of vehicles, okay, you are going to use more and more energy from the grid. Okay. So what will happen if we know that at present we have that immediate generation for the thermal power plant. So if you take more energy from the grid, what will happen under such a situation? That you need to burn more coal, so you are going to increase the pollution where the area where the power plants are located. Definitely you are going to make the area clean and green where more electric vehicles are being used. Understand? But so what happens? To avoid the issue of localized pollution which is taking place at the site of the power plants, what we do that we try to avoid this one. Understand? We don't use grid. Whether it is good, like if you can use a PV fail grid. Understand? And then you have a, let's say that I'm writing here boost converter with LPP. Yeah? LPP. And then you make the connection. Now this is a PV fail charging station. Remember that this type of charging station has a limited capability. If the capability of the source is limited, then what we have done, limited, we say that you design it for 100 ampere. Okay, and then each of these are drawing, let's say that 20 ampere. So 20 ampere only charging one is no issue. Okay, that is around 5% of that. 40 ampere, 10%, 60 ampere, you can see. So you are increasing the percentage. So what will happen? The requirement of the current like it will burden this source, and you will see that as you connect this vehicle, so during the transit, there will be a drop in the DC bus voltage. And if the drop in the DC bus voltage is there, so what will happen? You will have two possibilities. One is that if you let it drop, what will happen? So what will happen that under such a situation, you will have to use a charger which can operate with a wide variation in the input voltage. Okay, so the cost is going to increase. Okay. Wide variation in the input side. But if it is regulated here, so you have to use a charger which does not have that much of variation. Okay, does not have that much of variation in the input side. So the cost comparison you can make. Okay. So this is one case. Okay. So to avoid this, we are just connecting here. So under such a situation, what we do, we try to use some maybe a buffer battery or let's say an ultra capacitor element we can use here with a bidirectional converter, and then we connect it here. So what will happen? The moment you connect it here, you are going to draw more current. Also, there will be a drop in the DC bus voltage. So at that time, this ultra capacitor is going to supply the current, excess current. So you are able to regulate the DC bus. Is it done? Okay. So you can see that mixed resistor. Maybe like what will happen during the daytime? It is okay. Okay, during the daytime it is okay, but during the evening time also some comes to get the charge. So you can, with the help of PV panel, you can do it. So maybe like you are interested in using battery energy storage system. So what will happen when less number of vehicles are being charged? So the two processes will take place. One, that this battery will be getting charged, and so on, that you are charging the battery also, on the battery. And whenever the more number of vehicles, then you can use this the energy which is stored in this battery also to regulate this DC bus voltage. Okay. So this is a PV fed battery assisted or ultra capacitor assisted charging station. Okay. But maybe like of course like let's just suppose that you have energy storage, they also fail sometimes. So maybe like you want to use the facility of this. Okay. So it will be what? PV fed grid assisted charging station. Okay. PV fed grid assisted charging station. Grid assisted means you will not be using grid for all, and maybe during the night time you will be using it. Or maybe you will be using the grid together with this battery energy storage. So this is okay. So this ultra capacitor, what we have understand that the purpose is regulation of the DC voltage. There are other possibilities also, like you can use the flywheels. Maybe like flywheels will be larger for the size of light electric vehicle, but you can use it for the charging station very easily. Okay, this is lecture and VSI and flywheel. Okay, this is mechanical power. And its momentum is very high, its source energy as 1/2 j omega square. So what will happen? When everything is okay, then it is receiving some energy and it is constant. After some time, the balance will be maintained here. 1/2 j omega is stored here. Now let's say that you connect a load here. What will happen? There is a drop in the one voltage because it wants to draw more current. So immediately what will happen? The source side voltage is lower than the load side voltage. Okay, it is higher. So regeneration will take place. Because of 1/2 j mechanical is stored here, so it will take some time to drop down. But definitely speed will take time, but by that time it is going to submit the energy. So by this way, you are going to submit the energy to the DC bus to meet the instantaneous requirement or transient requirement of this charger. Okay, so you are able to regulate the DC bus voltage also. So this arrangement is called static equalization. Okay, static equalization, and this one is called dynamic equalization. Okay, this is there. So this is what the mixed energy storage system for the charging station. Let me go back here. So this is what the case is explained here. In which 10 vehicles are considered, and the drop is taking place. You see that one by one we are connecting the vehicle. Okay, here you see. When you connect one, there is some drop in the bus voltage. Connect next, again drop, again drop. So this drop is taking place with the connection of the different vectors. This is for short duration of time. We are talking about transient. Understand? But this is not allowed. So what we do? We use some buffer arrangement. This is what I explained you there. Okay, buffer, it could be under extra battery. So always it is required that we should regulate the DC bus voltage. Now one more problem is there. when you disconnect this load one, remember that they are going to consume more current, large current. They are not simple load. Okay, heavy current is front loads are there. So what will happen under such a situation? Under such a situation, what will say that this is a boost converter now from the photovoltaic panel, you can say. Okay, so the moment you disconnect the load, what will happen? Your current which is going to the inductor from the photovoltaic panel is coming or whatever it is. So it will take some time to fall down. So you can observe this curve here. Okay, go outside. This is the DC voltage. This is the by the time this is falling down, that your first DC increasing. You see, if it takes more time, so by that time, you can see that this voltage will increase more. So this is the problem of basically control. If you have a very good control, the voltage will be regulated. But of course, there are some limitations. Okay, so beyond that limitation, you have to think in a different way. So this type of problem, when a load disconnection is taking place, you can do two things. One, either this excess current, okay, why this excess current is coming? Because you cannot drop down immediately. So this will be operating for the regulation, off, on, off, on. So when it is on, it will be like this. When it is off, each cycle is storing resistance to the capacity, and no current can flow here. So the DC voltage is increasing now. That's the reason. So what you can do at the DC bus, you have the ultra capacitor. So with the help of bidirectional converter, you can bypass that energy to the UCs. Okay, so regulation can take place. This is one. Okay, external. Second is to the control. So you can adopt some control strategy, like fast control strategy, maybe sliding mode control, or there are so many things. Very good, like control. You can control the power level, which V square control or I square control. So with that, if you are able to make it flow very fast, let's say here, so by that time, what will be the rise? Maybe like only this much will be. So, yeah, how fast your control is there, you can do that. It may be like you can operate your converter in discontinuous mode of operation. So this is required that the DC bus voltage should be regulated. So with the help of control of this can do, with the help of external elements, let's say that 5 giga element, Doppler energy, or you can dissipate that energy also if you don't want to store it. Understand? For the time being. So depending upon the like how much the cost you want to make there. You can dissipate if you are not able to do that. Like these are the curves we showed that practically is popular here. So this is from my side. Now I'm open for the question. You can ask me the question. Madam, are you there?
Yeah, sir, in your last slide.
Okay, last slide. Uh, again,
Yeah, the ID, I think the red color graph. So the initially the first, I think first duration, it's going to be very high. The current of the red one, third, this below, sir, below this one.
yes.
Yeah.
Just let me zoom.
Yeah, the ID current is going to initially first very high value. The latter is going to be settled down. The transient error will be very high.
This one.
Yes, sir. The red line initially is going to be very high.
Yes.
So how to reduce that value? Because the transient errors is not accepting everyone. Because if you are using, I think maybe you are using some 10 kVA, but it's going to be 30 kVA initially.
Yes, yes. That's why I said only control is not there. Like with the help of control is the issue. Like there is one control strategy I have shown that you try to modify the reference. If you see this curve, okay, let me zoom it. What is happening? Here you see that this is the reference which is generated. Like you have two loop control. You see, one is the voltage loop and another one is the current loop. So if the DC bus voltage, when you disconnect the load, what is going to happen? The bus voltage is going to rise. So at that time you are sensing it. So this current loop is going to generate a current reference, and this reference is under such a situation is very, very high. So if you are able to reduce this current reference below faster, then what will happen? Because at the end, what is this? This current is going to follow that reference. Okay, accordingly you can realize the current. But if you make it very fast, drop down this reference, okay, and you will be able to force your control power electronic circuit to do this charge faster rate. So this is what I done. So we have done that we try to try to modify the reference, and for that what we have done, we have measured what is the output power and what is the input power. Okay, what is the output power and what is the input power? From that you see that VOIO and divided by the input side voltage. Then we have calculated what is the reference required for you. So what is your power requirement according to the control? Then we multiply that reference with the reference which is generated by this voltage because this was very high. Okay, so if you multiply and take the square root of what the variable is going to get, okay, that will be somewhat quite low. This modified reference is appearing here. You can see here this one. Okay, so this is making only. So that's why I said that we have to make a control in the power level. Basically, by doing this, we are doing the control of I square. Okay, indirectly we are doing the I square control. This is the V square control, I square control. Okay, this is your reference is V square of the voltage for that control part. Okay, taking the decision. So then only you will be able to regulate that DC voltage. This is from the control side. Otherwise, we have discussed this. Whenever the voltage is rising, here you see that whenever this voltage is rising, okay, whenever this voltage is rising, this DC control starts drawing this excess current to this submit here. So basically taking it out. So you are putting less burden over this. Here is the inductor. What is this one? This arrangement. Repeating. You can see this is the arrangement basically. This is the problem in that circuit. And this is your DC bus. So immediately one load you are disconnecting. Let's say that this load you are disconnecting here. So this voltage is increasing. And here you are having this panel. You try to reduce this current basically very fast. Otherwise, what will happen? The bus voltage is going to rise. Externally, or you can use the through the control, or you can take the help of both. Okay, but of course you have to propose some strategy. Energy management. You can think in that way. So, like all these points, what I put in these are some research topics. You can think over it. Okay. Any questions?
The transient peak is getting because of the inductor.
No. Transient peak is getting off because in each cycle of the operation, see, here you see that when you disconnect it, do you think that this current will fall down immediately? No, and you cannot keep this switch permanently off on. So what you can do that you completely turn it on. So this current will pass through this one completely. But if you do like this, maybe like you do not have sized your switch accordingly, it will burn out. Okay. So you have to draw it through some modulation strategy. Maybe earlier you were using continuous, now you operate this continuous mode of operation. Okay. But by this time, each time this switch is off, you are submitting energy to the capacitor. Sorry, this DC link capacitor. So the voltage in each cycle, it is increasing one by one, like see. This is the inductor current, and it is taking some time. And what you are doing, you are trying to regulate it to bring it down to zero. So with each cycle, with each of the cycle, the DC link voltage is increasing. Understand? Is the current maybe like you can use different level. Let me choose different color for this. Huh? This is the inductor current. Let's consider that. So this one is for the current, and upper one is the current IL, and then this one is upper one is your DC input. Each cycle is increasing. So how to select the control, that is very, very important. Okay, any other question? There are some, is there any message or, ma'am, are you there?
Can you suggest
Okay.
some methods to reduce that peak value? Because when I have developed one grid to vehicle charging infrastructure charging simulation, there I am also getting the same peak value. I have changed some input side capacitor value, output side DC link capacitor values, but it's not working. So can you suggest any technique?
Okay, Srinivas, actually, see, our strategy I suggested you that either you make some external arrangement, okay, that use some, let's say, if you don't want to use ultra capacitor, you can use power battery. So you bypass that energy to the battery. That comes under energy management. Okay, and we store that power battery. Okay, your work is done. Or you can use like a control, maybe like you can use sliding mode control, the MPPT. So if you with your boost converter, which is connected with the uh, your photovoltaic panel. So then you use some fast control strategies. Or if you don't want, you dissipate that one using arrangement of the dynamic braking. So whenever that voltage is rising, you set some reference level and separate control separately to dissipate that in the excess energy to the rheostat. These things you can do. Either you store it or you dissipate it. This is the two things you can do.
Okay, thank you, sir. I will try.
Okay. Is there any question? Okay, then I think there is no question. No? Yes, what is the controller can use for charging and discharging?
Sir, can you
Charging
explain
like
more
this.
about reflection charging?
Huh? Can you repeat your question?
Explain more about. Can you explain more about this reflection charging?
More about reflex charging. Okay. Actually, okay, let me see if I have some slides and I can explain more about the reflex charging here. Continue. See, in reflex charging, what happens? You can see here. Suppose that what you do that you make a continuous charging because generally people do CCCB charging. If you are making CCCB charging, what will happen? You see,
Sir, your
this is the
slides.
CCCB.
Sir, your slides are not visible.
Okay, now it is visible. Okay.
Yes, sir, no visible.
Okay. Moment. Suppose that what we do that we make a continuous charging. Huh? So in case of continuous charging, what will be the current? It is continuous, no continuously like this. Huh? But what the problem will be there, if you observe the battery temperature, it will start increasing. Understand? It will start increasing continuously. But we don't want this one. So what we can do that whenever that such a like when we see that it reaches to a particular level charging current, what we do? We stop charging. Okay? Yes. And so when you discharge it, whether you charge or discharge, the battery temperature is going to rise. So this is rising further. Then we set another limit also here. Okay, two limits basically. Like maybe like this is sometimes such like something like a hysteresis control. Two levels are there. Sorry, there's some problem with my screen. Screen display code off. Just a moment. Huh? There's a problem with my computer screen. I'm trying to. Huh? Okay, I can. Okay, sorry, it is there now. Hmm. So what we do here, yes. So what we do in this case is not. Sorry, just. So what we do that we see that there's a one level that temperature again rises whether the charge or discharge. So if we are now discharging it, it rises. So we check another limit also. Two limits. That this is the maximum limit, what it is allowed, and then another one is the maximum discharge limit. So you use two hysteresis basically here. Okay. And lower level is fixed here. Minimum E, minimum is fixed such type of limit. So you see that once again it reaches to this value, we stop discharging here. We stop discharging here. So now what will happen? The temperature will go down. Okay? And once it reaches to the minimum level, again the charging process takes place and then it rises. And the process follows in a similar way. Something like that. You can make it here. So again after that, the discharging here and then again it rises. After this and then again another slope like this, discharging and then it discharges. So this is basically what the reflex charging is. There. Means you keep a charge it and you discharge for a very short duration of time. This is what it is. And this is generally very good for lithium ion batteries. Okay, lithium ion batteries. This is very good.
Thank you, sir.
Okay, I think there is no question, no further question. So, okay then. So now I can stop. Okay, thank you a lot. Thank you. I think there is no other question. Which switching device are used for the same circuitry arrangement you will be using? Which type of components or circuit is required for the reflex charging? There are so many questions for the reflex charging. See, circuit element is
Thank you, Mr. Ritesh Keshri, sir, for this FDP. Sir, am I audible?
yes, yes, madam.
Yeah, yes, sir. Thank you, sir, for this informative session. You have given insights on electric vehicle definition, then pure electrical vehicle subsystems, possible configurations of supply system, and you have given insights on definition of battery charging and means of charging. Thank you so much, sir. It was indeed a very interesting session. Thank you so much, sir.
Okay, thank you, madam.
Sir,
Can I,
the participants, next session will be started immediately after this session. Okay, no gap will be provided. Okay, next session will be started immediately. Please stay online, dear participants. Thank you. Thank you so much.
Hello, Jariwala sir, are you there?
Yes, I have joined in.
Okay, okay. So dear participant, our guest had joined. So we'll immediately, sir, can we start immediately?
Yeah, we can start.
Yes. Over to you, madam, Lengade madam.
Hello, madam. Am I audible? A very good afternoon, everyone, and welcome to the third session of day 3 of this 1 week FTP on EHV, organized by AICTE College of Engineering, Pune, sponsored by AICTE ATAL, co-sponsored by SAE. This session will be taken over by Mr. Rushabh Jariwala, Functional Safety Manager, Eaton, India, E-Mobility Division. I take this privilege to introduce Mr. Rushabh Jariwala sir. He has over 20 years of industry experience, reliability, life cycle management across automotive, industrial, and avionics products. With embedded system, functional safety as his expertise, he has been instrumental in setting up ISO 26262 functional safety assessment strategy for e-mobility products. He is associated with high voltage electronics safety architecture strategy at Eaton E-Mobility Division for more than 3 years. He is involved with development of products like inverter, DC-DC, onboard charger for electric vehicle. At Eaton, he also streamlined industrial products SIL, that is Safety Integrity Level Assessment and certification process across engineering, supply chain, and manufacturing in line with IEC 61508. Prior joining Eaton, he was reliability manager at Whirlpool for India and steered warranty optimization programs. Also, he was associated as reliability and safety consultant at Honeywell for avionics products. Sir, I welcome you on behalf of AICTE College of Engineering. I request Mr. Rishabh Jariwala sir to proceed with his session. Over to you, sir.
Yeah, thank you. Let me share my screen.
Yes.
Mm, yeah. So let me know once you all can see my screen.
Yes, sir. The screen is seen,
Okay,
sir.
fine. Yeah. So hello everyone. I'm glad to know that okay we are actually discussing about these upcoming technologies and all that. So what I will be basically sharing is when it comes to this either electric vehicle or HEV kind of platforms, what are the aspects of the safety that we should look into, and what are the challenges about, and then what are some of the, I would rather say, key components and subsystems of the vehicle which fall into the safety criteria. So uh, yeah, so that's what we will be discussing. And please, I think regarding your questions or something, you can just interrupt in between. That's fine, or we can take the questions later into the at the end of the session. Okay, so first, so this would be what we'll be discussing, that okay, when it comes to the battery uh, electronics, like what kind of challenges are there, and then what are the major concerns, and what are some of the standards and regulations, and so on. So if you see, we while moving from the gasoline uh, to the electric vehicle, it actually brings in very unique advantage as well as challenge. So what it is when it comes to the gasoline vehicle, it's gasoline has a very high energy density, and then it's but the conversion of the energy density to the motion power, it's just something like 15%. But safety point of view, uh, if you see, hello, somebody want to say something? Hello. Okay. But safety point of view, if we see, then it is like by now it is proven. We never have any sort of reservations or doubt that okay, there would be something can go wrong onto the our either petrol or diesel car. And because it is now, it has came to the point where we know how to handle it, and think it is like it is a trusted. But when it comes to the Leon battery, mainly for the electric vehicle and hybrid electric vehicle, so its energy density is actually speaking very low. But when it comes to the motion power efficiency, then what we achieve is almost like 60 to 80%. So that is comparatively very high as compared to the gasoline. But then when it comes to the safety, the perception of the user is still, it is like not, I would rather say that safety point of view, it's still, there are some perception is okay. How about, is it really safe? Because what we are dealing with is now onto the next gen of the vehicle. It is like almost talking about 400 volt DC, or even it can go up to 850 volt DC HV battery. And then some of the HV loads like sometimes inverter and DC-DC converter and some of the things. So it is directly driven on this particular load. So there, if we see, then safety point of view, it is a bit of the concern. Like let's say if somebody want to do the servicing and then this HV battery is still live, then this is almost like a I would say very catastrophic event it can turn out to be if the safety is not taken care into the design of the vehicle. And then other thing is the Leon batteries thermal management itself is quite complicated. So we'll just look at what is happening around, especially because the main driver of the main thing component of the any of the electric vehicle, battery electric vehicle, is the lithium ion battery. and typically it is like small cells of the battery. We pack it, and then it becomes like a very huge HV battery with a high power capacity. That is what happens. But if you see the Leon battery on its own, if somebody has deep knowledge of what are the some of the real pitfalls of this battery is, so it was commercially in 2006, the the Dell, they actually moved from the NiCad to the lithium ion battery into the laptop, and then around due to around 4.1 million notebook, that was actually replaced because the laptop, during the charging or sometimes during the operation, the Leon battery can catch the fire, and it will just simply, it will be few flames would be there, which is very much risky, and that's why they actually recalled this. And then as we moved forward, it was not like Leon battery was not used. Leon battery started getting into the notebooks, and then into the mobiles, and then every other place where the compact battery solution was needed. And then the lithium, it also got into the Dreamliners, the basically Boeing commercial plane. And there, the lithium ion battery, they actually found out one big couple of big issues, wherein even the grounded plane, when it was going through the normal power up, it one of the battery pack, it caught a fire, and then like that some incidents was actually was noticed and observed. And the main root cause what was, as per the publicly available information, what we know is that it was something to do with the battery manufacturing method that introduced some sort of defects into the HV battery pack, and then due to that it can result into the overheating and temperature, which leads to the fume. Now imagine something flying on couple of 1,000 feet, and then one of the battery pack catch a fire. Means it's almost like a end of the story. So that is how at least it again came into the picture. This lithium ion batteries are really safe enough. And then in the same time around, the automotive started adapting the lithium ion battery packs into the EV cars and so on. And there are some incidents, but I'm just noting, just want to highlight the one that happened very recently in 2019, where a couple of neo, almost 5,000 SUVs, they need to be recalled because this battery pack in certain condition, it can overheat and can catch fire. So this is the state of the, almost I would rather say it has reached to the state of the art, but then a small mistake either into the manufacturing or either into the thermal management of the battery pack, or during the charging and discharging, if one do the very high discharge, then also it is a problem. If one do the very the charging to the full capacity, then also it is a problem. So this is overall one of the safety concern piece that is still there. And then like that, if we see, then there are other issues also, but this is the one which is the most prominent. And ideally speaking, if we see, then most of the HV, there are handful of HV battery, Leon battery manufacturer who knows how to what to do into the different things. So that's why things are okay. But this is something, if we are designing a new platform, or we are designing a new kind of battery management system, and this is the something that still it is a need to be looked carefully by anyone. Then let's move forward onto this, that if we see the electric vehicle, then actually speaking, as compared to the traditional automotive car, it has handful of components, and so it's like there is a electric motor. There are even technologies in which electric motor is integrated into the wheels, but I'm just showing that, okay, let's say electric motor for the propelling of the wheel, and then there is a inverter which is typically run onto the HV battery, and then bidirectional converter, sometimes DC-DC converter, auxiliary loads, HV battery, and battery charger. So in a way, if you see, then it is pretty simple system that what we have. But within this, there are some novelties that we introduce because of the altogether change into the technology. And then now let's look into what are some of the major hazard point related to the electric vehicle. So the one of the most prominent one, what I say, is unintended vehicle movement. So battery electric vehicle actually brought in a very different kind of challenges. That is, like, there is no, it is so silent that there is no actually natural feedback to the driver that either he has started the car, and that sometimes lead to the, like, unintended movement out of driver's consciousness. And then other thing is, if this either inverter or e-motor get powered due to some fault internally, then that can also start propelling the car. So because it is internally, if you see, then HV battery pack is always live, as compared to if we see the gasoline technology, in which the petrol need to go through the ignition cycle, and after ignition cycle the power will be generated, and when power is generated, motion power, then there is a very good audio feedback to the driver that, okay, now engine started churning up and it makes a noise. So driver has a very good, if you see, observation that, okay, fine, like, even if I don't want car is starting, but when it comes to this electric vehicle, then it's a bit different. It's not that simple, because any false start, then it can also lead to the unintended vehicle movement. Then another thing is, this is a new kind of hazard, what I would say, low energy stranding. So the into the electric vehicle, one has to be very careful, the OEMs and whoever is responsible, to show the state of charge remaining into the battery while driver is on the road, because nobody knows, means one has to estimate that, okay, when is the nearest charging station, and accordingly look at the SOC and then say, okay, I have to make a mandatory stop, or I can still continue my journey, which is different than the gasoline. Because in gasoline, if you see, at least in any country's network, normal urban area, the, like, the petrol pumps and diesel stations are available at least every other 2-3 kilometers. So one has to, even if it indicates the wrong like, volume of petrol remaining, and one gets stranded onto the road, then there is a easy way to get out. But when it comes to EV, if the state of the charge remaining is shown incorrectly, then one can actually be stranded onto the road, because charging points are not easily going to be available. And so this is what is the another hazard which actually comes with the electric vehicle, that to, if it indicates wrongly the state of charge remaining more than the actual capacity, and then it can actually put the driver into the difficult position, and sometimes it can even lead to unintended vehicle movement. Then other one is energy storage rupture and toxic gas management. So the HV batteries, when they, I think somebody is, if you can mute, it would be good. There is some background noise continuously happening.
Yes, sir, I'll check.
Yeah, please. And now it's okay, I guess. So energy storage, rupture, and toxic gas management. So now this is a very unique kind of hazard because the Li-ion batteries, when they go through the charging and discharging process, it actually release some uh, toxic gases. Although it is a small in amount, but still it releases. And if the venting system is not designed properly, then and if these gases enter into the passenger compartment, then it can be a very, I would rather say, dangerous to the passenger if the amount is little bit high, or because this is a continuous process, charging and discharging, at least the discharging during the drive cycle, and then so on. So that's another a new kind of hazard which is there, which is when it comes to the gasoline vehicles, then it was not that much, those things were not that much toxic. And then other thing is, there is a, either it is a petrol or diesel, it has its own little the smell that gives a immediate indication to the passengers that okay, there is something wrong. But the Li-ion battery, the gases are odorless, and that's what creates another, if you see, inherent issue that okay. Another thing is the energy storage, integrity and protection. So that is again around this, all these HV components, which how to store it, and then integrity protection from the crash hazards and all that. Okay, just give me a moment. I'll do. Okay, and then the after that it comes to the another hazard, that is elimination, mitigation, and potential thermal and explosive events. So this again is related to all of this. And then shock protection, which is, it is normal, it is there into the gasoline vehicle also, but there are some components which can be highly sensitive when it is exposed to the, sorry, there is some disturbance, then it can create a problem. Means if it is directly hit by another vehicle or by other object, then it can directly create a problem. So there is some, so these are what I am just first explaining, the top level hazards related to the electric vehicle. And then now we'll go into detail of each of the one. So the very first one, if you see unintended vehicle movement, so this we discussed that, now if it is mainly to do with the inverter, and I think e-motor is just following to the inverter, but when it comes to the inverter design, then one need to kind of think that active driving possible mode. So when the driver is actually speaking, just want to say okay, start the vehicle, at that point of time, if there is a problem with the inverter or somewhere into the design or logic, and if it just simply release the torque immediately, then that is actually one sort of hazard, which is and it is having enough energy. So like HV battery, and then what we are depending on to the converter is uh, just to share the things. So that is one thing. And then active driving possible mode. So this is one thing where let's say if one has actually uh, because these vehicles, they don't produce any noise. What is important is that when it is actually into the park, one has said that okay, I put it into the park mode. then indeed its inverter and some other and e-motor gets de-energized, and they are basically, I would rather say, not providing onto the power. That is important. Otherwise, there are some incidents and recall that has happened in which one thinks that okay, I have parked the vehicle, but internally there was some software or hardware issue, and then it just vehicle starts moving on its own after the driver is leave the vehicle unintended with a key on into that. So that's what is one thing. Then uncommanded over or under torque delivery to motor. So actually, any of the BEV or the HEV, this brings is a little bit a different kind of hazard, means as compared to the normal electric vehicle, because normal gasoline vehicle, because any of the electric vehicles are all fly by wire, and into the fly by wire the driver is pressing the accelerator, but its equivalent signal is going to the either the inverter, and then inverter is further developing a torque based on that, and then it is going to the e-motor. Now there are so many things in which what we are doing is just processing the software and algorithm of the based on the equivalency of what accelerator pedal input we have received. And then what happens is that if there is some error into this, then one can actually generate a more than required torque or less than desired torque, and it ultimately can result into the unintended acceleration and deceleration. And that is how our dependency on software, actually speaking, goes very high in this kind of technology, although it has matured. But this is something for when every new component related to torque management is delivered. This is something very important. And then signal to the driver when exit the vehicle if the vehicle is still. So this is what I just explained. Then false indication to the driver of the vehicle direction. So yet another, this is like, because inverters, they also do the actually work as a generator when it comes to we want to actually store the energy from the braking, and then the same e-motor, it can basically we can turn it goes reverse and whatever way. So due to this, there is a into the design one need to take care of this, that vehicle always drive into the intended direction, and there should be enough check and balance within the software for that. And then movement of vehicle propulsion system prevented unintended when external charging. So this is something important, that when the vehicle is going through the charging process, at that time one need to make sure that it does not allow the vehicle to start and apply the torque. Otherwise, it creates a little bit complicated situation that one can drive away the vehicle with a charging cable locked into it, and it creates a kind of like danger to the some damages to the property. So again, this is one need to think of when designing the onboard chargers and inverter and its coordination and so on. So now let's move to another hazard, that is like shock protection. So here what happens is protection against there are two type of, I would rather say, the shock protection that one need to think of is protection against the direct contact. So especially the compartments of the like HV battery, it should, and its cell should be designed such that okay, nobody there is it's absolutely not possible into the normal circumstances for the human being or the service personnel to touch the live part, because HV battery is always, if you see, it is very heavy charge is stored, and even one direct contact is something to take away life of the person. Yeah, want to say something? Okay, and then other thing is, if you see onto this protection against the direct contact, so within the vehicle, there are so many bus bars running, which typically carry the current into the any into the any range of 1000 amperes. So how to design a system in which, although all the complete vehicle is all metallic, but still it is designed such a way that these things remain isolated from the metal body where the passenger is going to directly contact it, and then so that it does not create a shock hazard to anyone. So that's something. And then protection against the indirect contact. If you see, then this is what is how to maintain the isolation resistance, and then some other things. Plus, one more thing, what also is important, that how to charge the HV battery compartment, how to place it, I would say, sorry, how to place it. So ideally speaking, most of the OEMs, the way they design the compartment for the HV battery is into the such a way that it is away from the direct impact of the crash. And so if you imagine, then probably, yeah, placing it uh, to the foremost front of the vehicle may not be a good idea, versus placing it at the rear end of the vehicle may not be also be good idea, because that two area can be directly hit. But basically, if you see, then lying down the battery packs such a way that it is below the passenger area, where something over here, then that seems to be a sweet spot. But then there are some challenges with respect to this. So anyway, so this is what is something important, that even placement of this energy storage components plays a critical role, so that like when there is a crash event or something, then it does not get a direct impact. Otherwise, it is that itself is enough to catch a fire. Means person may not die out of the crash event, but due to the fire or electric shock, it can actually be a more problem. Then one more thing is like the post crash. So there are certain, like I would rather say design rules around this, that after the post crash event, within certain seconds, the HV power should be cut off from the all the loads, so that any emergency responder or even somebody who wants to help out the passengers of the vehicle don't get exposed to the live part, or the of the which actually has the high voltage carrying. So that is another requirement. And also onto the car, there is a need to design some sort of mechanism where the emergency responder can actually de-energize the vehicle first. And so that is a, again, in addition to the automatic protection, there are some like manual mechanisms also given to make sure that one can actually de-energize, one can isolate the loads from the HV battery. So that's what is, if you see, something one need to take care, and which is important from the shock protection point of view. And this is where all the things like the uh, like a team into the structural dynamics and all, who can play a big role in selecting that okay right design of the vehicle, and also assess that either the component placed into the certain area gets least damage when it comes to the extreme crash kind of events. So now let's move next to the next topic. So retention and HV battery placed shielded from the contact with the roads. So this is another important thing, that it cannot be directly, it should be placed such a way that it does not hit by the objects onto the road while vehicle is moving into the normal condition. And then into the post crash, the HV battery shall remain attached and not enter the passenger compartment. This is in a way obvious, because if the 400-volt battery, if it is pushed into the passenger compartment, then it is directly going to lead to the electric shock if one comes in contact with that. Then post crash mechanical shock, the state device shall remain in its mounting and components shall be inside the boundaries. So that is more to do with how to design it such a way that they don't get the components don't get misplaced, and then we pose a danger of electric shock to anyone. Then other thing is post crash. So mechanical integrity should be maintained. So that is kind of important one. Then electric vehicle safety hazards. So here energy storage, rupture and toxic gas management. So this I explained it. So how to, there are some things where there are some mechanisms to actually warn the driver in case the the thermal and then under vehicle operation, so including operation with a failure, vehicle occupants shall not be exposed to any hazardous emissions from the HV battery. So in use, no rupture, leakage, venting, fire or explosion. So this is again related to battery. And post crash, there should not be any electrolyte leakage. So what it mainly is this HV bus bars and all that should not be leading to the condition where it comes directly in contact with the main electric the body of the vehicle, where customers are going to touch it to either open the door or maybe to take out the to the passenger from the crashed vehicle. Post crash mechanical shock, so this one is related to this. And now let's look another one, low standing uh, uh, charge. So this is where it comes that driver warning of the low HV battery state is something important. Otherwise, what happens is that, as I explained it earlier, the driver might keep on running the electric vehicle, and then suddenly it just all the HV batteries start charge. It is showing, let's say, 30% remaining, and then suddenly it goes to 0% in next moment. Then driver would be into the problem. And imagine this happening to the somebody who has invested into very high-end electric vehicle like Tesla, and then this kind of things happen. But onto the high-end cars, what typically they have a very good mechanism is that even they map that, okay, what is the nearest using the GPS, that okay, what is the nearest location of the charging point, and based on that one, either driver can comfortably reach to its destination, or they need to visit the charging point, and those kind of things automatically explain, means give a nice indication to the driver. But for all of this, the battery state of charge remaining based on the uh, duty cycle behavior of the driver, and also based on some some intelligence of, okay, what is the uh, like uh, I would rather say traffic conditions onto the road, or if somebody is driving uphill. So those kind of things one can actually there are some OEMs who has done it, who kind of based on the driver's destination, they predict upfront from the road conditions and the territory of the road, and that okay, fine, the SOC state of charge remaining will be enough to reach to the destination, or it can actually, if it is going to create a problem, then inform the driver upfront. Which, and this kind of challenges were not there especially into the gasoline vehicle, because that was very simple. A lot of gasoline stations are there, but here that is a new kind of challenge what need to be managed. Okay, so now I will just explain some of the critical components and then what are some of the safety related features related to that. So the one I'll just start from here. So there is a kind of like pyro switch next to the HV battery. So that HV pyro switch, what it do is it acts as a small I would rather say fuse. Let's use the word fuse, but fuse with contactor. Imagine that way switch. That when there is a crash event, then inside the pyro switch there is a small from all the loads. So that's what happens onto this by the pyro switch, and that is a very important device considering the crash protection. And other thing is next one we'll move to the HV battery. So by now we have discussed onto this. That HV battery has one specific thing, as I told you, the thermal management and other things that it need to be taken care. But its main responsibility, I would say, is BMS, battery management system. And so battery management system is the one which actually monitors the cell and then continuously checks that whether all the cells are with a right state of charge, and then during the charging how much to allow it to charge, and then thermal management and other things. So the other thing, if you see, let's move to this, the DC-DC converter. So typically DC-DC converter, it derives the voltage from the high voltage and then feed all the LV low voltage load. So that is more to do with the some of the radiator fans, and then the one that is related to at the console plus powering all the ECUs and all that. And related to DC-DC converter, the main uh, the safety point of view, what need to be taken care is AC to DC. DC to DC means the isolation between the HV DC and the LVDC, because that is something important. And then another thing is during the charging process, DC-DC conversion process, it should not lead to the its power electronic should not lead to the thermal runaway kind of event. And for that one need to design the cooling channels and all that in a right way. And then the other one is, if we see, then there are some things like let's go to the OBCs. So OBC, onboard charger, it needs to provide the protection that to the battery management system, HV battery, so that it does not charge more than needed. And then also it needs to have the certain thing, like there is one thing that is active discharge. So active discharge would be generally needed in most of the HV components which is driving the power from the HV battery side. So let it be inverter, let it be DC-DC converter, and let it be the onboard charger.
Salaries delay. Salaries delay. Actually, Corona time la salaries delay.
Can you please mute? Hello.
Yes, sir. I do, sir.
No, there is some noise coming. Okay, now it's okay. Yeah, thank you. So active discharge is the one which, for all of these components, which is deriving the power from the HV battery. So they have a bulk capacitor to kind of smoothen out the voltage once it comes inside for consumption. And this bulk capacitor, they are, if they, it has enough energy to even give an electric shock to the any person. So active discharge is a function expected out of all of these loads is when there is a crash event, it should discharge all the energy remaining into the bulk capacitor into very short period of time, and that is typically 5 seconds. And so that one need to think about when designing such type of components, let it be inverter or one that is DC-DC converter or sometimes OBC as well. And so after that, let's go to the next one. So these are the some of the standards related to this EV development cycle. So into the design, one should consider the standard like FMVSS 305. So it gives certain guidance about what should be, how the brake should perform, how the inverter should perform, what kind of mechanism should be there to indicate the fault and all that, which is generic, but still that is important if one is thinking about releasing the commercial vehicle into the US market. There is another. So another one is UL regulation 100/94/95. So that is I would rather say global, which similarly actually define certain requirements for the EVs. And then of course ISO 26262 is there for the functional safety. So that basically takes care of how to select the architecture, how to do the software design and so on. And then there is a, when it comes to the testing, so there is a SAE J1766. So recommended practice for the electric and hybrid electric vehicle battery systems crash integrity testing. So how to perform the crash integrity test. So there is a standard around it, and it provides a kind of good guidance of how much of the impact load should be tested and how to assess the damages post the crash event, and then what are the things that one should actually I would rather say observe at high level. Then logistic. So here it comes the as we looked at one of the case that the HV batteries, they are very sensitive to even the vibrations and the mechanical shocks and all that. So there is a SAE standard J2950. It actually explains that if one is transporting the HV battery packs, then what are the precautions one need to take when transporting it, and so for the assembly, and after that obviously into the once it is into the vehicle, then its integrity need to be maintained. But this is more specifically transport from the HV battery supplier to the OEM if it is transport into the way of the HV battery pack, and then into the production. So there is a standard IATF 16949, and that is more about safe manufacturing practices to maintain the product safety. So that is for that. And then ISO 26262 also gives some guideline around what are the things that should be taken care to to do the production of the high critical safety components. And then to do the disposing of the HV battery, so there is a V directive. So that is another thing that Leon batteries are environment point of view, they are very vulnerable if they are discharged, if they are just thrown out into the either open land or into the water resources, and it is enough to what I read somewhere that okay, even 5 or 10 Leon batteries, if one puts into the river, then that river water will become unusable. So it's a so sensitive topic on its own. Then let's go to next one. Yeah, so these are some different standards. I would rather say that uh, basically makes it possible to say that how HV batteries, EV vehicle should be, different things should be worked on. So it starts with testing for the Leon cells, and then crash integrity testing. There is a SAE standard for it. Then there is a for the battery safety, again one standard from the SAE. Then fuel cell safety. So this is more to do with the for the hydrogen fuel cells. So that is a different thing. And then the validation testing of the electric vehicle batteries. And then FMVSS 305, we already discussed about it. And battery at use testing and all. So as we can see, there are a couple of standards just dedicated to the HV battery. And it is something important, and because it demands that level of attention. Now we will move little bit into the we looked at one standard, that is ISO 26262, which is mainly to ensure the functional safety of the vehicle. And this particular standard, if you see the way its importance is that OEM would typically tell into the I would rather say as a part of the product specification that I want the product with SLC, SLD, or SLA, B, like that. Now, what does it mean in reality is like this. So all of this SL is a automotive safety integrity level, and it mainly defines that okay, the safety function, its a probability of failure should be low. So how far low? So this is some numbers that okay, if it is a SLD function, then its probability of failure should be less than 10 to the power minus 8 per hours, and which is actually speaking it has to get a very low number, need to be proven. And then on the other side, the architecture need to be having something known as the single point failure metric and latent point failure metric. And based on the SL level, that number varies. So now I'll just give an example that what does it mean by the single point failure metric of the 99% for the SLD. So what actually it means that for all the components that is involved into the delivering the safety function. So safety function can be as simple as that the torque management, let's say, for the inverter. So all the functions that is involved into this delivery of the torque management, out of that, only 1% of the component failure modes can be allowed to fail such a way that it can compromise the torque management. Remaining 99% of the component failure mode has to be detected, and there has to be a mechanism to bring it to either a safe state or indicate the driver or whatever. But this makes it very complicated from, I would rather say, design and architecture point of view, because typically there would be not less than 1,000 components onto the electronic board of this kind of inverter. And what we are talking is out of 1,000, roughly 1% means no more than very small number, that component's failure can be allowed to compromise the torque management. Remaining all should be detected. So that's how. And then there is another one, that is latent point failure. So these are like combination of two failures, if it can compromise the safety function, then that should not be anything like less than 90%. So only 10% failures or two failures combined together can compromise the safety function. Other rest 90% of the total failure modes has to be detected, or there has to be a mechanism to invoke the safe state. So this is what, if you see a very high level idea of the ISO 26262, but in reality, where it helps is that OEM can clearly communicate to the supplier that I want this particular component to be ASIL A, B, or C, or D. And after that, there is a standard. In that one, it is clearly written that, what to, how to design the system, and then what kind of failures can be allowed, and this SPF and LPF metrics that need to be followed, and so on. So this is the, if you see the typical process of this functional safety. So one is, one need to first define, so that, okay, what is that one wants to design, and then after that vehicle hazard analysis need to be done. So that includes all the scenarios, that if you say the take case of the inverter, then when the vehicle is driven, when it is not driven, at high speed, low speed, all of the things, and then understand that, okay, if something can fail, then how it impacts the vehicle. So that is called the hazard analysis, and based on that one identifies the the hazards criticality, and then assigns a ASIL rating for it, for the safety functions. And then it goes into more like the next level of the defining the functional safety concept, under which one defines that, okay, for which hazards one need to indicate the driver, or how many need to have its own safe mechanisms, and so on. Okay, so that are some things related to, I would rather say, the safety analysis. This is a very deep subject. Typically for a product to do this kind of assessment, it takes minimum 6 months to 1 year to do the proper assessment at the vehicle level. And then for the component level, it would be still, it is not more than months, into the units of months it takes. Then second one is like what one should do between the production point of view. So this is how the safety concept need, functional safety requirements and all that need to be matured. And but I think the A, B, and C sample is more to do with when it comes to the automotive life cycle, this component development life cycle between the OEM and the supplier. So B sample is something where it is just a prototype kind of thing, and then C sample is the production intent, in which all the software is matured and so on. And then D sample is that it is just now there will not be any changes expected into the product, means from the design point of view, and it is ready to go for the mass production. Okay, so now I just want to kind of summarize. So if we see, if one wants to design either it is an electric vehicle or hybrid electric vehicle, then it needs a close coordination between all the systems, like electrical, mechanical, and electromechanical, to ensure that everything works as expected and nothing happens other that is not expected. And then for anybody who is a small, I would not say small or big, but any company who wants to introduce a product into this space, then it needs a significant investment of time to understand the regulation landscape, to understand all these safety requirements which are more than normal design requirement, and then how to really design those things into the components or what, and then functional safety compliant system. So it's a overall, if you see, it's a significant efforts that it takes to design a safe and reliable and efficient, either it is a battery electric vehicle or hybrid electric vehicle. Okay, so I think that's all from my side. I would leave it open for the question answer or something from the team.
We'll take up questions, sir. Thank you, sir. Any questions? Sir, there's a question here. In what way testing of electric vehicle is different than IC engine vehicle?
Yeah. So if you see, as I explained you, this is comparatively a different, because the into the IC engine, the post crash scenarios, the way it need to be assessed is very much different for the EV, because we have to see for each of the component, either post crash, any of the isolation has not been breached, any of the components has not been misplaced from its original position such a way that it can impact the driver. And obviously other thing is, see what makes from vehicle dynamic point of view, what makes the EV a very different as compared to the IC engine is, from crash point of view, I will first explain and then go into the normal fuel efficiency and all that. So crash point of view, the EV vehicles are comparatively very light into the weight. So the crash dynamics actually changes a lot, so that one need to have a very good, sufficient framework to protect the components. And then if we see the other testing, like, power efficient, from the efficiency and pollution and some other point of view. So as you know, like electric vehicle, it's I would rather say pollution is not at all a question, but when it comes to uh, testing for its efficiency at the different loads in different temperatures, different driving cycles, that is a very different, means it's a complicated as compared to normal IC engine, because here even if we change one e-motor, an inverter, basically if we change one of the thing, just change the supplier, then a lot of things change, because the way the runtime losses can be calculated, the way the e-motor demagnetization need to be calculated for one supplier to another supplier of the similar e-motor, it actually changes, and then it impacts directly onto the testing the efficiency and so on. So this way it is different. There might be a lot of other differences apart from this, what we need to look into the standard. Then
Yes.
the question is,
Tools
okay,
used for maintenance of electric vehicles.
yeah. Used for the maintenance of EVs. As I had worked on tech as a technician for Honda, we had a special tools of rubber for maintenance of the Honda Civic. Yeah, you are right. So see, that is quite expected, because here we have to, at each and every step, the first thing we have to continuously think about is the safety of the service personnel. And that's why this, either we think of rubber tools or whatever, that is important, because uh, EV vehicles, once something is opened from chassis or anywhere, it is absolutely, at least the service personnel should not be allowed to touch anything with the bare hand, because there can be a live charge or there can be a residual charge onto that. Then which embedded platform is used for taking safety measures of HEV. So see, I would not say there is something like a specific embedded platform on its own, but it is more like if we are for the high ASIL rated systems, if we are selecting the controller, then even the controllers are ASIL rated with certain features onto it, which supports the high automotive safety integrity level. So that's how it starts. And then as we go up into the software and architecture and system architecture, so again it basically goes back to how to design safety for multiple things, mainly electric shock isolation, and then availability of system and so on. Anything else?
Sir, embedded platform used for taking safety measures.
Yeah, that's what I explained.
Okay.
And then,
I think
okay, what precautions should I take if I suppose I purchase an EV vehicles? So see, what we generally get commercially, and that is it has gone through all the testing. So I would rather say, safety point of view, if those things are not there, then our agencies like ARAI will not allow it to come onto the road. But if from consumer point of view, if you think, then this kind of features of the state of the charge and app to find the charging stations, and then the most important thing is the charging protection itself, because that is, if one is thinking of typically in Indian scenario, that is where it lands up, that we have to charge it within the home, or sometimes into the office there are charging points. But then what they have done to ensure that during the charging something unexpected don't happen, so those kind of things will be there. Is the crash test norms are same or different for the EV compared to conventional vehicle? So there is some difference, because the structure of EV, as I told you, it is a lightweight, and the post crash scenarios, the way it need to be assessed is different. So yes, there is a difference, and that's where I showed that particular some of the standards to test the battery electric vehicle for crash and all that. So in that one, that these differences are if one goes through, then one can find out.
I think the questions are almost done, sir.
Okay.
Uh, sir,
Yeah.
let me thank you, sir. Thank you
Thank
so
you.
much
Yeah.
for
I hope it
highlighting.
was useful for the audience. Thanks a
Yes,
lot.
yes, indeed,
Yeah.
sir.
Yes.
It was you have rather covered the various aspects and approach of electric vehicle safety hazards, and of course, as you said, it will be useful and informative for the audience participants here, research scholars here,
Yeah.
to
Yeah.
explore more, sir.
Sure.
Thank you so much. On
Thank you.
behalf of AICTE College of Engineering, I would like to once again thank you, sir, for your time, and
Yes.
thank you so much.
Sure. Thank you. Okay.
Thank you, sir.
Bye.
So we come up with the end of day 3. The feedback and attendance link is shared to you. I request to fill up that, and we'll be resuming again tomorrow as per the schedule. Thank you everyone. Thank you so much.